I hope you have started interesting discussions now that you will continue over lunch and in the afternoon. We have now heard about research policies at the governmental level from 3 different research intense and strong research countries in Europe. This morning's last speaker has a broad international experience, sharing his time between Massachusetts Institute of Technology, the MIT, and Stockholm University. He was awarded the Nobel Prize in 2004 for describing why the quarks, the tiniest building blocks of the atomic nuclei, why they are never seen alone but always glued together. It's a pleasure to welcome Professor Frank Wilczek, professor in theoretical physics.
Hi.
So welcome.
Thank you.
So we're looking forward to hear your views on what favors successful research.
Okay, well, my talk's going to be a little bit different. I'm going to talk about a particular research subject, but one that is very, very central, and I think needs a different kind of thinking and long-term thinking that this audience may want to be engaged in. So it's a great question of philosophy, understanding our position in the world, as well as a great scientific question to understand how and if mind emerges from matter. For most scientists, the working hypothesis is that it does. Neurobiologists hope to understand mind by studying human minds and animal minds by studying brains. But in fact, we've come to understand even in our everyday experience with computers, that information is physical and that it can be embodied in several radically different ways. And therefore, minds that are things that process information should also be able to exist in several different forms, emerging from matter, as I'll discuss, in several radically different platforms. So that's my topic, future minds. So I'll talk about digital computers, quantum computers and simulators, idealized neural nets, and biological neural nets, which are 4 emergent kinds of minds that are going to be very important aspects of the intellectual, economic, and cultural landscape in coming years, and certainly important research subjects. So let's start with the most mature and familiar, but I want to remind you, extremely revolutionary technology. That's the digital computers that this presentation is being presented on, for instance. So this is a modern Intel processor on the inside. It's about the size of the top digit of a thumb, and it contains the following specs. It's capable of running on a clock. Of course, it turns over, it makes new operations 3 billion times a second. That's what 3 gigahertz means. Costs less than $1,000. Not a lot less, but less than. And it works on a lot of stuff. It's not only fast, but has a lot of things that a big sketchboard on which it works. So that's a truly remarkable technology that which is the basis, of course, of many impressive devices and economic developments. On the other hand, we can see things that are not quite optimal. This QPI, quantum path interconnect, is a measure. I won't go into the technicalities, but it's a measure of how fast information is being put through the system. And it's, as you see, it's not very different from the clock speed, which means that even though you have all these units, they're not working in parallel or very efficiently. The thermal design power, how much heat the thing generates under conditions that can occur in practice, is 130 watts. That's a lot to have in this little space, and that causes a lot of problems in applications. And perhaps most profoundly, the size of the individual processing units, the transistors, is basically 45 nanometers, which is getting to be not much bigger than molecules or individual atoms. So we're getting to the limit of how small things can be without radical changes, as I'll discuss. Now, the ideas that go into these strange new minds rely on clear and powerful understanding of how matter works. So let me just remind you that the transistors, the technology that goes into this kind of device, into modern computers, modern information technology, is all based on the fundamental understanding of matter in quantum mechanics that was developed purely by intellectually driven curiosity research in the 1920s and 30s. And it would be literally unthinkable without that understanding. Now, since smaller means faster and cheaper, we need continuing innovations to make smaller and smaller devices and smaller machines. It doesn't work this way. It needs new ideas at every step as you scale things down to make them smaller, cheaper, and faster. Progress has been extremely rapid now for many decades. It's been encoded in something called Moore's Law, which says very roughly that all those things, the size, the expense, and the speed, increase by about a factor of 2 every 2 years. And that's been happening since the early 1960s. That's going to, however, be very hard to maintain for basic physical reasons. The basic physical reason is simply that present-day bits, the zeros and ones that encode the information, almost always involve either separating electric charges or aligning spins. So here's a little picture of how zeros and ones appear inside your computer. You separate charge by a little bit, so you have positive and negative charges, and they can be separated in 2 different ways. So that can represent 1 and 0. For spins, you can have them point up or point down, and in this way, encode the information and manipulate it. However, this is where the size that I mentioned comes in. When there are only a few electrons or spins, the rules change. The basic rules of how physics works change qualitatively. And this brings us to quantum bits, also called qubits. This is a frontier of research where it's a wild frontier. Right? This is not a mature revolution. This is a revolution that's still very early on, and it's not clear how it's going to come out. So we enter this strange new world. We're forced to, if we're going to keep going fast, smaller, faster, cheaper, dominated by quantum mechanics. It's a difficult world to work in, but it's also full of promise. Let me say a few words about those 2 aspects. But again, I want to emphasize that we can't remove quantum uncertainty. You can't undo the laws of physics. We must make the best of it. So the simplest two-state quantum system, the analog of something that's either 1 or 0 or up or down, is quite a different object from a classical bit. Because when you get down to atomic sizes, there's quantum fluctuations, quantum uncertainty. You can't pin it down to either be 1 or 0. Oh, I'm sorry, this is out of order. Let me. Okay. When we measure the, let's suppose that we have a spin that can be either up or down in quantum mechanics. It's not simply up or down. We can measure either the spin in the x direction or in the y direction or in the z direction, 3 different directions. And we find independent probabilities for whether it's up or down in those 3 different dimensions. Therefore, we need 3 numbers instead of just a choice of a 1 or 0, 3 continuous numbers to describe these probabilities. The qubit is a much more complicated object. Now I have to go back. When we go to 2 qubits, then we can pick either of the 3 directions independently, so there are 9 probabilities, or we can leave 1 bit alone and compute and measure the other one. That's 6 more possibilities, and now we need 15 numbers, which is significantly more than 3. And you keep going. To describe n qubits, we need 2 to the 2n minus 1 real numbers, or if that's too abstract, we start with 3, then we go to 15, then 64, 128, and so forth. Numbers, not just ones and zeros, but numbers to describe that the behavior of that many qubits. This gets big very, very fast. Some of you may know this story, but it bears repeating, the story of exponential growth. The inventor of chess, who may have been Persian, may have been Hindu, may have been a Viking, I don't know. In any case, it pleased the ruler so much that the ruler wanted to reward the inventor of chess and asked what the reward should be. And the very clever person who invented chess said, well, we'll do something that's appropriate to a chessboard, and we'll ask something modest. So we'll start with 1 grain of rice on the first day to fill 1 square, and then the second day, 2 grains of rice, the third day, twice as many again, 4, and so forth. The king said, that seems like a very paltry reward, a few grains of rice. But the inventor said, that's fine, that's what I want. And so they started, and the first few days, the king felt kind of sorry for this poor fool who was very clever in some ways, but very foolish in others, and just had a few grains of rice. But then, after a couple of weeks, the stacks got bigger and bigger, and the king got very embarrassed and chopped off the head of the inventor. That this is the miracle of exponential growth. This is what drove Moore's law, and now in terms of qubits, you get exponential growth. Each time when you add 1 more qubit, the space of information gets bigger by roughly a factor of 4, not 2. So thus, qubits are extremely powerful potentially, but they're very delicate. The fact that they're so rich means also that if you tickle them a little bit, it affects a lot of all these probabilities. So they're very different. We need to protect them from the outside world and from each other. They have to be carefully controlled. But of course, in order to do any operations, any manipulations of the information, any computations, we need to let them influence each other. And it wouldn't do us much good to have a black box that was doing very clever things left alone because it's delicate. We also want to put information in and out. So physicists and engineers are struggling with this kind of duality that you want, on the one hand, to take care of these very delicate, precious, very powerful information carriers, but on the other hand, you want them to do things and also to do things that you ask them to do. So there are several different ways. Atoms being addressed with lasers, trying to use light and its polarization or other properties instead of spin or charge. Circuits that use superconductivity that can be addressed electronically. Computing with braids, this is a more exotic thing that I'm particularly fond of because it anyons were something I named and kind of invented, and they've become very popular. In any case, we don't know which of these technologies is going to win out in the long run. And it's quite possible that one will leap ahead, then another will catch up because they have complementary virtues. The technology, going in the digital technologies, the earliest machines were mechanical, Charles Babbage's analytical engine. Then there was an era of vacuum tubes, and now smaller transistors that, although they have the same name, they're qualitatively different devices through several different generations. And also the memory devices have gone from magnetic tape to thumb drive and so forth. Here's what the inside of a qubit looks like. This is a machine created by Google, a quantum computer with 53 qubits. Not very high quality, so they do fluctuate, and their computational abilities are limited compared to the ultimate potential. However, they achieve something called quantum supremacy, which is that with that device, you can create behavior which cannot be simulated in a reasonable amount of time with a reasonable amount of resources by a classical computer. So it can do things that classical computers can't already. On the other hand, so can a carbon atom. So can one carbon, that's one atom quantum computer, because it can do things that no classical computer can do, namely calculate how carbon atoms interact with light and do that very efficiently. So really, I think the concept of quantum supremacy needs to be thought about very carefully. It's not the case that suddenly classical computing, digital computers are going to become obsolete and irrelevant. Far from it. General purpose quantum computers are still a long way off. A partnership between classical and quantum computers, where quantum computers do limited tasks that they're especially good at, maybe a way forward. Also quantum simulators, a quantum version of wind tunnels, sort of more sophisticated versions of the carbon atom being a very good way to compute the behavior of carbon. Those are also exciting research frontiers. So there's going to be an evolution and ecology, not a revolution and displacement. So I really think we shouldn't talk about quantum supremacy. It's also not politically correct. So we should talk about quantum advantages in different particular applications. Okay. The next kind of strange new mind topic I wanted to discuss that is and will continue to be a focus of extraordinarily fruitful research is the topic of connections. These are neural nets, both artificial and natural. So digital computers we're familiar with. I showed you the insides, and they shuffle zeros and ones, or the quantum computer does these very strange parallel operations. Biology thinks different. The units are much, much slower. The clock rates are nothing like billions of computations per second. Humans can process perhaps a few thoughts per second, not billions. On the other hand, they have much higher connectivity. I'll show you a picture momentarily. And they have massive parallelism. So they have many, many things computing at the same time, where we saw that was a weakness of the digital technology. So here's layers in the retina. Here's layers in the cerebellum, and in many parts of the brain, especially the large parts, you find an architecture that's repeated over and over again with layers and cells that communicate up and down between the layers. This strategy of working with slow units and a layered architecture and exploiting parallelism in some way, although it's very different than what we do in digital computing, works amazingly well. I mean, here we are. And people have taken inspiration from this, tried to build strange new minds inspired by biology. This is the basic unit, an artificial neuron. I won't belabor the technical details, but basically it takes a number of numerical inputs, weights them, so multiplies each input, which is a continuous number, by another continuous number, adds them all together. If the sum is above a threshold, it fires, and otherwise not. So sort of inspired by biology, but much simplified. Units like that can be wired together because you can take the output from one and feed it as the input of another, and you can make layers, again, kind of inspired by biology. And these kinds of architectures, these kinds of ways of putting artificial neurons together have recently been an engine driving progress in machine learning. That's quite dramatic. So famously, you can have neural nets that recognize cats within pictures or faces, or even learn to play games that were thought to be pinnacles of human intelligence better than humans. So chess, Go, and recently World of Warcraft? No, StarCraft. The key to it is that with this architecture, you can learn better weights. The basic idea is you have inputs to the units that look to the external world. So look at the images or look at the data files that you're trying to learn from. And you put it through the neural net at first with just some more or less random choice of weights, and see whether your output matches the desired answer. Does it correctly classify faces or cats or something? And if not, the unit reports an error. The preceding layers evolves in such a way as to correct the error, as to make the error less by changing its weight to that connection. And then you can do it again, because the previous unit now also knows what it should have done, so it can tell the preceding unit how to do better. how to make its weights better. And this very simple idea called backpropagation, where you learn better and better weights, is what's driven the revolution in machine learning. Okay, I see I'm... but that's not the end by any means. Biology has networks which aren't, although they're layered and have that kind of architecture, they have connections that go both ways. So they're feedback, and these neural nets influence themselves. They think about themselves, if you like. They're examining what they're doing, and that's our experience. Every talk is improved by having a baby, and here's a baby learning to recognize itself. It'll be a milestone in artificial intelligence when you can have a unit that looks in the mirror and says, that's me. But we can do that virtually and build up to the real thing. Okay, my time is up. I'm getting the message. so I will quickly close. That on the material side, we also have the model of biology that's telling us we can do better. The way brains develop is quite different from clean rooms and the elaborate, delicate technologies that go into current computer design. And this is also using the magic of exponential growth to make many, many units and many, many connections. This is physics and engineering of the future that will bring in self-reproduction, self-assembly, and self-repair, things that are hardly employed in current day engineering. So to summarize, strange and powerful new minds of several kinds are on the horizon. There's enormous scope for creativity. We don't know what the path forward is. We can see that there's tremendous distance to the horizon and glittering prospects. And I think the way to get there is to think long-term and cast a wide net. So I hope the ministers will help us do that. Thank you.
Thank you very much for this interesting topic. I think there's a lot in media about quantum computers, not so much about the biological systems. Is that your view too?
Well, recently there's been this spectacular development of quantum supremacy, which I hope I've gotten the message across, is a little bit artificial. I mean, but it is true that
we saw the machine.
The engineering, I mean, is artificial as a goal because it's not doing anything useful. It's just doing something that a classical computer can't do. However, the engineering of quantum computers is advancing very, very rapidly. It's following some kind of Moore's law curve. We'll see if this kind of exponential improvement can be sustained over years. But if it is, then the ultimate potential of quantum computers will catch up with classical computers and be useful for a variety of tasks.
So as you point out, we sure need fresh minds to
We need fresh. That was the subtext, and I'm glad you got that. I hope everyone got that. This is one big area or meta area of scientific progress that's representative of problems that are curiosity driven in the first instance. How does mind work? How does it emerge from matter? What is how can information be embodied physically, but then becomes a whole sequence of scientific problems of different kinds, bringing in all different areas and involving connections and cross-disciplinary approaches that really would be very hard to anticipate.
So what would be the most important preconditions for young researchers? If you think at governmental policy level now, what would be the most important preconditions to have all these young minds?
Yeah, I think one very important aspect is that young people should not be too burdened with making grant applications and and just worrying about how they're going to live and how they're going to eat the next, and whether they have someone looking over their shoulder who's going to possibly cut off their research projects if they don't show tangible results in a year or two. I think it's very important for young people early in their career to have some kind of stability. So that's one aspect. On the other hand, there are others. Of course, there are other conditions that we can identify. One, I think, is that there should be a community. A community in which the young people can get to the frontiers of knowledge and get a sense of what the possibilities are and take advantage of the expertise of the leading figures in the field and get inspiration from that. So stability, community.
And this
I had
has
something,
been mentioned.
You warned me this, so I made some talking points. Stability, community. Oh, feedback. Very important. Okay, so feedback that's not of the form, your grant is terminated, but of the form, this is maybe an opportunity you're missing. This is something you're doing very well, and you should encourage, feedback from more experienced scientists, maybe from scientists whose interests are a little off from the immediate research project of the young person, I think can be enormously valuable in keeping them oriented and not wandering sort of aimlessly and feeling alone.
This has been mentioned. The Swedish minister mentioned the career paths stable, and I think it was from the Netherlands. We were talking about the ecosystems. And
yes, a community, ecosystem. That's very much the same idea.
Where you would also have the feedback and also the centers made in Switzerland. Getting
and in the community, it's really important in science that the community is international. So within any reasonably sized subfield of physics that I know very well, but also in other sciences, the leaders are dispersed throughout the world. There are a small number of them, and it's very, very important to maintain contact with them, bring them in for visits, for colloquia, for things. Just keep. So
are there any particular strategies you would recommend to have this?
Well, Sweden,
to attract,
I think,
international researchers to Sweden. You came here yourself. So
yes, I came here.
How did we manage to recruit?
Well, Sweden has a lot of advantages. It makes it very attractive. First of all, English. Everybody speaks English. Makes it very easy for a large segment of the international community, which that's the lingua franca these days. It's a very pleasant place to live. I'm not going to flatter you by telling, but it is, and it has some wonderful scientific traditions. Of course, it has the Nobel tradition, but also the VR, the Wallenberry, and just a tradition of thoughtfulness and mentoring that I think is very special. Not perfect, but very special.
So what could we do better?
Okay. Well, you could improve the weather and coax the sun to come out. I think, well, I mentioned it in a scientific context, but it's also in a societal context, that one thing that makes Sweden attractive is that many of the worries of everyday life are less. That people don't have to worry about healthcare so much, getting insurance, just basic living standards, and also seeing living standards that are well spread through the society. But there's a balance between stability on the one hand and complacency on the other. And this, I think, shows up especially in research when, as I mentioned, I think for young people, stability is really, really important. They have to be able to take ventures that may not pay off for 5 or 6 years, right? But on the other hand, old people sometimes need a little kick. Older people, once they get tenure, it's really important. Well, a kick is the wrong concept, but to have mechanisms so that people can explore more widely and not sort of be stuck in redoing their thesis or whatever over and over. And so they encourage.
So stability at the beginning of the career and more adventure
a little more.
along the road.
I think in general the Swedish system is doing very, very well, but maybe some thought and fine tuning along those lines. Right?
Thank you very much, Frank Wilczek. A big applause. I will.
All right.
Vänta. Wait.
Oh.
So, Frank, you have already tasted the food of the Nobel banquet.
Yes.
Here is, so you can go home and make it yourself.
Okay, that'll be a challenge. All right.
I will also hand you some chocolate
this is great.
Nobel medal, so you can.
This might help me to pay off some bets.
But I mean, you're one who can now both eat and have the medal. I think that's.
Yeah, but
So
I'll try not to eat the
applause.
medal. Okay, thank you.